Up to this point, we have talked about process control, controlling the process. Now we're going to venture into process capability. How capable is our equipment in producing to specifications? So, process capability refers to the ability to consistently produce parts that meet engineering specification requirements, even though variability exists between parts. Process capability bridges the gap between how our process is operating and how it should be operating with regard to what the design engineers want it to operate. So there are several process capability indices. We could measure hundreds or thousands of parts to see if any part exceeds specification. A better and more reliable method is to take a small sample, like 50 parts, and use statistics to determine what percent of products will meet specifications. Again, we're not talking about control limits once we go into process capability. Process capability measures are statistical calculations using the average, standard deviation, upper specification, not control limits, and lower specification limits to determine whether equipment and processes are capable to produce parts to engineering specifications. The first capability index that we use is a thing called CP, not CPK, CP. In many cases, the process variability is sufficient to meet engineering specifications, but for whatever reason, the process average is not centered in the middle of these specifications. The CP provides a value of what the process capability would be if it could be perfectly centered in the middle of the engineering specifications. So let's say our process is here. Now, if we look at the width of our variation with regard to engineering specifications, things look good. But because we're running here, we have some problems with our capability. What the CP effectively does is it pretends, it doesn't really change it, but it pretends that the process is actually perfectly centered. This distance is still the same as this distance, but we artificially moved it to the center to say, you know what, if we could fix the average, how capable would our process be? Notice here I'm using specification limits. These are not control limits. This is just what the engineering people want. Upper specification limits, lower specification limits. Just some comments. Because the CP is simply a measure of the specification width divided by the overall process variation. Overall process variation is 6 standard deviations. It does not account for where the process is located within the specifications. I've talked about that already. In the above illustration here, both bell-shaped curves would have the same CP value because the width of the distribution is the same for both, and the width of each bell-shaped curve, distance from tail to tail, here to here, or here to here, is the same. It does not account for where it sits in the process. Here is the formula for CP. You take the upper specification limit minus the lower specification limit divided by 6 times the standard deviation. And for the actual exam, I would give you the standard deviation because it's a bit difficult to calculate on one of those simple calculators. Here's a CP calculation example. Let's say that our lower specification, not control limits, is 10 and our upper specification limit is 22, and we determined our standard deviation to be 2. What is our CP? Well, you just take this minus this, 22 minus 10, divided by 6 times your standard deviation. You come out with 1. If you have a CP equal to 1, it means the distance from here to here is the same as our specification limits. Not the location, just think in terms of distance over distance. CP equals 1 could also be here. Why? Because this distance from here to there is the same as the distance from here to here. Or even here, this distance is the same as this distance. So therefore, the CP equals 1. Notice that the distance from tail to tail remains unchanged in these 3 images. Remember, CP equals 1 means that the tail-to-tail distance equals the total specification width. Here's another example. Specifications, again, 10 and 22. Standard deviation is 1. We do our calculations. This minus this divided by 6 times that. We come up with 2.0. It is 2 because it is half as wide as this, or in other ways, this is twice as wide as this, and so that's how you arrive at 2. This is also a CP of 2 because, again, CP does not take into account where it is within the specification. It could even be here and still have a CP of 2. In fact, you could even have your whole bell-shaped curve outside here and you would have a CP of 2, although you'd be producing 100% defective product. Notice that the distance from tail to tail remains unchanged in these three images. Remember that CP equals 2 means that the tail to tail distance equals 1/2 the total specification width, or you could say it the other way. The specification width is twice as wide as the tail to tail distance. Let's do a little bit differently. Let's say our specification is still 10 and 22. Our standard deviation is now 4. We do our calculation, this minus this, blah, blah, blah. We come up with a CP equals 0.5. So here's what a CP of 0.5, it simply means that the width from tail to tail is twice as wide as your engineering specifications, and that's how they come up with the 0.5. CP could also be here or even here. Notice that the distance from tail to tail remains unchanged for all three images. CP equals 5 means the tail to tail distance equals 2 times the total specification width. Or you could say the specification is 1/2 of what my tail to tail difference is, and there's your CP equals 0.5.